So, welcome everyone to this week's Origins Colloquium. It's a pleasure to welcome Marina Kunkel to give the talk this week. Marina did her undergraduate studies at University of Toledo in Ohio, and then was a PhD student at the University of Michigan, working with Lee Hartman. She had postdoctoral positions with Kevin Covey at Western Washington and at Vanderbilt with Ivan Stassen. 3 years ago, she joined the faculty at University of North Florida and is continuing, with here, a great research in stellar astrophysics and spectroscopy. Within the Sloan collaboration, she has a number of roles. She is the chair of the Young Stellar Object Working Group and is also the survey coordinator. So it's a pleasure to welcome you, Marina.
Right. Thank you very much for having me. So to get started, stars produce emission across the entire electromagnetic spectrum. And looking at these spectra, we can determine a number of fundamental stellar parameters. For example, looking at the precise features that we have in the spectra, the spectral lines, we can determine the temperature of stars. And looking at the shape of the lines, the overall broadening that these lines have, we can determine surface gravity. And of course, we can determine a whole bunch of other things, such as metallicity, rotational velocity, radial velocities. But temperature and surface gravities are considered to be the most fundamental parameters that stars have. And using these parameters in combination with each other, we can determine quite a bit about stellar evolution. So temperature is a proxy for mass. The hotter a star is, the more massive it tends to be. And surface gravity is a proxy of radius. So the lower the surface gravity, the larger the star is going to be. And since a star of a given mass and age is going to have a particular radius, by analyzing where all the stars are in the spot, we can tell quite a bit of stellar evolution. Now, this is a Kiel diagram. This is a spectroscopic version of the more familiar to everyone HR diagram. But what's special about it, it's unlike HR diagram, which is done photometrically, Kiel diagram is not affected by extinction, it's not affected by multiplicity, and it's not affected by any of the other things that affect photometry. So this is a much more direct way to probe stellar evolution. So spectroscopy has revealed itself as quite a powerful technique because of this to analyze the properties of stars. And over the decades, there have been spectra of several million stars that have been taken, tens of millions, hundreds of million even. And in particular, I am involved in one spectroscopic survey, which is Sloan Digital Sky Survey. And what the survey does, it has two spectrographs. One of them is apogee, which is a near-infrared spectrograph in H-band and has fairly high resolution. And the other spectrograph is BOSS, which is optical, but it does have somewhat lower resolution of only 2000. And both of these spectrographs are mounted both in the northern hemisphere and in the southern hemisphere, which provide comprehensive coverage across the entire sky. And also, as part of targeting efforts, SDSS has really made sure to include pretty much every single type of stars that are out there. I don't think there's any source type that has been avoided in the targeting efforts. There have been many various working groups that try to make sure that we are as comprehensive in our coverage as possible. And so in its operations, SDSS has obtained spectra on the order of 3 million stars and counting because operations are still ongoing. So having all of these data, how do we extract their stellar parameters? Well, the way it's normally done is through template fitting. So you try to throw in all of the atomic physics you can think of, how a gas of particular composition at given temperature and pressure would produce light, what types of features it will have. And you will do it for every single combinations of temperature and surface gravity and composition. And afterwards, after you have this synthetic library of stellar spectra, you take your data and you try to evaluate which of these templates matches your data the best. For example, here you can see that we have a fairly good agreement, and here you don't have as good of an agreement, so likely these will be the conditions for the star. And you take a star and you compare against every single template that you have in the library, and then you go to the next star and the next one and the next. Because of this, unfortunately, spectroscopic template fitting is not the most efficient methods to extract stellar parameters because say it takes you 1 second to read in the data and the template and to process them however you need to process them and to find the goodness of fit. But you have something on the order of 6,000 templates to fully sample the underlying parameter space in order to find the best one. And then after you compare against all of the templates, you move to the next source, and it doesn't matter how similar or different the next source is to the previous one. You still need to redo all of these reading operations all at once because you don't know a priori what the parameters of that star are going to be. So even if it takes 1 second to calculate the goodness of fit between a single pair of real data and the template, to process something on the order of 1 million sources, it will take something on the order of 200 years. So it's not the most efficient way. Of course, you can try to improve it. You can run multiple processes in parallel with one another. You can try to make your code more efficient so it runs faster. But still, once we are dealing with these large spectroscopic surveys, it just becomes difficult to scale up after a certain point. It worked well when we had only a handful of spectra that we need to figure out what they are. But once we're dealing with surveys that obtain thousands of sources every single night, it just doesn't scale well. So we need to have something that is a bit more efficient. But even this could have been tolerated had this approach to work well. Turns out that atomic physics is really difficult, and in order to create faithful synthetic spectra, you need to understand everything about how the gas could produce light. You need to understand the wavelengths of every single transition that could possibly occur, both atomic and molecular, even the transitions that you cannot reproduce in a lab because the conditions here on Earth are very different from the conditions in space. You need to understand the oscillator strength behind every single transition. You need to understand the opacity that these transitions will create on the continuum. And so as you can see, the synthetic spectra don't always reproduce the data very well. There are some transitions where we do understand them better, that we can reproduce the data, but in other places, the comparison becomes less faithful. So by trying to match against the synthetic templates that are not a perfect reproduction of the data, this introduces systematics to the parameters that we derive. Not all stars are created equal. For some of this is less critical than for other stars. For example, red giants and some of the main sequence stars inhabit a parameter space where the transitions that occur in the atmospheres of these stars are much more well understood. So in the process of deriving stellar parameters, Apogee, for example, has been able to extract pretty reliable parameters for red giants, parameters that have been calibrated to something like astroseismology to confirm that we are actually looking at particular temperature and surface gravity that we need. But for other stars, it becomes much more challenging. For example, pre-main sequence stars, they are really, really messy. They have many more molecular features in their atmospheres, which are much more difficult to characterize. Plus, pre-main sequence stars are fewer and further between, so they're not quite as well studied. And also, young stars introduce a whole variety of other features to them. For example, young stars tend to be very magnetically active, and they have large spots on their surface. These spots can cover more than half of their photosphere. So because of this, you are not dealing with just one single temperature across the entire surface. You're dealing with a blending of two different surfaces with two different temperatures. And our models can't really account for that. So in the past, we tried to extract parameters for young stars using traditional template fitting, and the results of this were less than promising, let's put it that way. So there were various gaps where the stars seem to avoid particular temperatures. Not all of the surface gravities were physical, and even the main sequence was in a somewhat odd space. So there still was meaningful signal in the surface gravities that we have been able to extract. For example, if we were to separate out everything into different populations, the population that we knew to be older, for example, Orion D, had higher surface gravity than some of the younger populations. So we can see a meaningful gradient as a function of age. But because of these deviations between the actual parameter that we extract and the models of stellar evolution, actually trying to figure out how everything should relate became a non-trivial task. If you have to make certain assumptions to try to correct for these systematics, you don't always know if these assumptions are valid or not. So we need something that is not only fast, but we need something that is a bit more robust in the parameters it is able to extract. And nowadays, we can approach it not necessarily just from the standpoint of theory in a top-down sort of way of figuring out everything that we know about stars and then try to reproduce the data using this model. We can use something that is a bit more empirical and data-driven. And one of the ways that we can use it to take advantage of this wealth of data that we have is through using machine learning. How machine learning works is I like to think of it as matrix multiplication. So you have your data and you know what are the stellar parameters in this training set. So you have been able to extract temperature and surface gravity for these stars using some sort of method before. And you take your data and there has to be some sort of matrix that you can multiply your data by, such that by the end, the output of this multiplication would be just the two parameters that you're trying to predict, and these parameters would be close to the original labels that you have had for the data. And the difficult part is figuring out what should go inside the matrix, figuring out all of the weights of the model that you're going to use. And the way that you would train this model is first you assume random weights, and then you pass your data through this model. And by the end of it, you get the predictions for temperature and surface gravity. And the initial predictions are going to be absolutely awful. But for some sources, it's going to be a bit less awful than for others. And so you go back and you try to adjust all of the weights, trying to keep the performance on the stars where you had slightly less awful performance, and to try to improve all of the other sources. And you do it over and over and over and over again. And eventually you have calibrated weights in your model such that if you were to pass any spectrum through this model, you will get something that resembles temperature and surface gravity compared to what you had in your initial labels. And this would work not only for the sources in your training set, but it will work for all stars, even for the sources that the model hasn't seen before. So, but in order for this method to work, we need to have a training set. We need to have sources for which we do know temperature and surface gravity. So how might we get that? Well, we might start with classically derived template fitting parameters. Since the red giants and some of the solar type main sequence stars seem to work quite well, and they have been previously calibrated to astroseismology, we might as well use them. There hasn't been issues with these parameters, so that will be a good starting point. If we want to extend this parameter set to other areas, for example, if you want to go to M dwarfs, there the parameters derived from template fitting are a bit worse, but there have been some boutique analysis trying to extract temperature and surface gravity from some select group of stars. And based on these boutique analysis, there have been there have been some scaling relationship that has been established that the star with this set of infrared colors would have this particular temperature, this particular surface gravity, this particular metallicity. So it's not ideal, but it will give us a starting point for these parameters for the M dwarfs. For pre-main sequence stars, it's a bit more challenging because young stars tend to evolve very quickly. Their evolution is very rapid, and that's why we particularly want to understand what are their fundamental parameters in order to observe this evolution directly. But we do have models of how stars evolve. We do have the isochrones that young stars are expected to follow. And for a given combination of age and mass, a particular star would have a specific temperature and surface gravity. But temperature and surface gravity are not the only thing that depend on age and mass. So do the colors, and so does the luminosity. So since photometry is readily available for all these sources, we can take their colors and magnitudes and interpolate them across the isochrones. To be honest, the results of this interpolation are kind of awful because there are many things that could also affect the photometry of young stars, well, photometry of any stars, not just mass and age. It could also be extinction. It could also be multiplicity. It could also be a whole slew of other things. That's kind of why we wanted to have a spectroscopy in the first place. But as a first stab at trying to derive labels for all these sources, this would unfortunately have to do. If we were trying to come up with a model to extract stellar parameters just for the pre-main sequence stars, this probably would have been the end of it because the model that you can create is only as good as your training data. This training data is not ideal. Again, we have various gaps. We have some unphysical surface gravities. But we're not trying to create a model just for the pre-main sequence stars. We're trying to create a model that would work for all stars. And here we have lower mass main sequence stars, where the model could learn, well, how spectra of different temperatures look like. And here we have red giants, from which the model would be able to learn, well, this is what effect surface gravity has on stellar spectra. And so to some degree, the pre-main sequence stars really all need to be there to give the model some awareness of this specific parameter space, but it will be able to learn much more effectively from the things that surround it. So by training a model on all of the sources simultaneously, we can create a self-consistent model to extract temperature and surface gravity for all stars, including the pre-main sequence stars, because it will be calibrated to more evolved stars that kind of surround them. And after that first model, we have been able to significantly improve on the parameters in our original training set. We have been able to significantly improve our temperature. Surface gravities were still not that great, but taking these temperatures and taking the ages that we have produced from the isochronal interpolation, we have been able to refine our labels. We have been able to reinterpolate surface gravity, and we have been able to do it a couple of different times to continuously improve our models of determining stellar parameters for the pre-main sequence stars. And so after several of these iterations of different models, this is what we have been able to come up with. So here we have temperature and surface gravities for pre-main sequence stars that we have been able to extract using our models. All of these sources are color-coded by their photometrically derived ages. So the photometrically derived ages were just derived from colors and magnitudes, nothing to do with spectrum. And the model has been able to derive surface gravity just from the spectra without relying on the photometry or anything else. And these lines are the isochrones expectations of how surface gravity should be able to evolve with age. So as you can see, the ages that we can infer photometrically and the ages that we can infer spectroscopically from surface gravity end up being completely self-consistent. And so one could argue just how much we could rely on any particular model of the isochrones. Some of them are better, some of them are worse, none of them are completely perfect. But at least nowadays we can use spectroscopic parameters in conjunctions with these isochrones, and they produce self-consistent results with photometric estimates. So that's great.
Can I ask a question? So which
Yes.
model, which grid of isochrones have you been using mainly, or
So this is primarily MIST.
missed? Okay.
And we have been able to do this not just for pre-main sequence stars, but again, we have been able to work with the entire parameter space of all stars that have been observed within SDSS. So we have extended the sources that we are able to characterize from brown dwarfs to AB stars, pre-main sequence stars, red giant stars, even hot subdwarfs and white dwarfs. So again, this is fairly representative of all of the sources that are being observed by large surveys. And the nice thing about being able to do this once for one set of data is that you have the stars that are the same no matter when you observe them, what instrument you observe them with. So the next time that you observe the same star, it should have the same temperature and surface gravity. And we have been able to test these parameters. They appear to be self-consistent across multiple observations. We are also able to estimate uncertainties. We are able to see the scatter in the predictions from multiple epochs. And the scatter in the predictions, if you take the entire sample as a whole, the scatter appears to be perfectly Gaussian, with the width of that Gaussian being pretty much exactly 1 sigma based on the uncertainties that we measure. And we can also take the sources that we have observed here with one instrument, and we can try to transfer the predictions as labels for another instrument. Because again, the stars are going to be the same no matter what we observe them with. So we have been able to train the model for optical spectra for SDSS. We have been able to create similar model for apogee spectra within SDSS. We have been able to create a model for Lemos spectrum. And here you can see some of the differences in the KL diagrams in terms of the parameter space that they do cover, but that's primarily due to the targeting strategy for both surveys. For SDSS, there have been efforts to make as comprehensive selection of all different types of stars, whereas Lemos has been a bit more opportunistic. They were primarily targeting brighter stars across the entire sky. But otherwise, the parameters that are being produced by for both of these set of spectra are very self-consistent with one another. And we wanted to see just how far we would be able to push this approach. We wanted to see if we would be able to apply it to Gaia XP spectrum. Now, Gaia technically is the largest spectroscopic survey to date. It has been able to produce spectra for 220 million stars that are spectra for which are publicly available. The downside is that these spectra are extremely low resolution. Here you can see it just has a couple of points across the entire optical spectrum to the degree where it's difficult to call it spectra. It's more of photometry. So we were kind of skeptical how far we would be able to get. Certainly, we should have been able to get temperatures, but we didn't know how well surface gravities would be able to work. But turns out you can actually get surface gravities from these XP spectra quite reliably. Because if you were to try to isolate sources to just a narrow range of temperatures, but looking at different surface gravities, you can see that there is quite a bit of difference between them. We normally think of the effect of surface gravity as the broadening of the individual lines. But turns out you also have continuous opacity variations at different surface gravity, and our model has been able to extremely precisely pay attention to what is a continuous opacity is without even having access to parallax or any additional information other than just the spectra themselves. So we have been able to process all of these 220 million sources and determine temperature, surface gravity, and metallicity for them. And these predictions are reliable enough that we can just basically select this corner of parameter space where pre-main sequence stars live. And we are able to see where all of the nearby star-forming regions are. So you can see there are a couple of famous regions such as Orion, Perseus, Scosen, and a couple of others, Vela. So this helps us with just minimal effort to see the census of all of the nearby young stars that are across the sky. And looking at surface gravity specifically, if we were to zoom in on a couple of these star-forming regions, for example, here we have Orion and Perseus, and Taurus is somewhere here, and we were to color code all of the sources by surface gravity, well, I don't know how familiar you might be with these regions, but the redder points are the younger stars, bluer points are the older stars. And this overall map of the star-forming history of these regions that we can infer from surface gravity, it's very self-consistent with what we can infer from just photometry alone, from our understanding of studying these star-forming regions over the years. And this is, of course, not the only way that we can search for young pre-main sequence stars. We can also use photometry to make a selection of all of the young stars in the solar neighborhood as well. And looking at this map, you see the exact same star-forming regions. I will blink back and forth. You can see the selection ends up being fairly self-consistent. The difference here is that here we needed to do a very, very careful selection of trying to account for the extinction, trying to carefully avoid the binary sequence and all of the red giants in order to minimize contamination. So it took quite a bit of effort to create this map. Whereas here, it was literally just drawing a polygon in the parameter space of temperature and surface gravity, and we get all of the same sources selected. But there is a bit of a difference in these underlying selection. And again, I will blink back and forth. Pay attention to this region right over here. So this populations of stars hasn't really been previously known about. So what are these sources? Well, turns out they tend to occupy a fairly coherent set of distances. So these sources are found at the distance from around 150 to around 200 parsecs. And they do tend to have fairly coherent set of ages. They're all around 20 million years old or so. But take a look at their velocity dispersion. So these sources have velocity dispersion in excess of 20 kilometers per second. And that seems weird because we know that young populations tend to begin their lives as dynamically cold. They inherit the same velocity as the molecular clouds from which they form, typically on the order of a kilometer per second or so. Over time, as they get older, they increase their velocity scatter, they heat up, they begin dissolving into the galaxy. And over time, they will dissolve. But still, when you have a very large and very massive population, the core of it will stay coherent for something on the order of 100 million years. You would still be able to see this population because all of these stars are still going to be moving to one degree or another, even if the population itself is not gravitationally bound. Here, though, we have more than 1,000 stars. So it's a fairly massive population, as massive as some of the other very famous star-forming regions. And it is fairly young, 20 million years. We should still expect to see coherence in the velocities for all of these stars. But the fact that we don't means that this population has been very recently relaxed, probably violently so. It's more than an order of magnitude more relaxed than any of these other young populations with similar age. So potentially, as we try to figure out what has actually taken place here, we will be able to see a brand new look at how the stellar populations like this may evolve over time. And the fact that we still see it to be so tight in the plane of the sky is an evidence that disruption has had to have been fairly recent. All right, so to bring this to a close, so nowadays we have a fairly comprehensive and self-consistent grid of stellar parameters for many millions of sources across from many different surveys across the entire parameter space. And specifically for young stars, this is the first time that we have um, reliable enough surface gravities to act as independent proxy for age. So we are able to understand stellar evolution just using spectroscopic data without relying on the photometry. And all of this has only been possible through empirical approach to data analysis using machine learning. But to kind of bring to put a punctuation on this, machine learning is not be all and all of any type of data analysis, and it's not be all and end all of stellar spectroscopy either. It helps to provide empirical set of measurements for all of these stars. But now we actually need to do the hard work and try to understand why our models work the way they do, what specifically they pay attention to, why the stars function the way they do. Like a century ago, when we have been able to derive the empirical grid of spectral types, that was acting as a stepping stone to understand the fundamental stellar physics. I hope that as we dive deeper into all of these parameters and try to understand all of these stars in more detail, we can further our understanding of stellar physics even more, and not just understanding stars, but stellar populations as well. All right, thank you.
Thank you very much. So that was a very nice overview of this program here, and there's lots to think about and discuss. So I suggest we structure the discussion in perhaps in three phases. One is the methods of how what this machine learning algorithm is working, and so we make sure we understand it. And there are probably questions there. And then you have interesting results on the YSO distribution and kinematics, perhaps. And then this last point you make about the implications for understanding stellar evolution we can come to. So are there questions on for the sort of, I mean, I have plenty of questions, but if people have questions on the methods, should we say it like that? I mean, I could start by the parameter. Well, there's a training step, and then there's the results step. So you're training. Let me make sure I understand this. First of all, does this machine learning method have a name? Is this is not what should we call it?
So I mean the names of the final models are ApoGNet, Boston, GaiaNet, so they're not very inventive names, but
Okay.
generally the underlying approach is using neural networks.
Right, to say ApoGNet, but well, that brings a point. So you have a model that's trained on spectra from one instrument at the moment, but you mentioned it can be cross-applied to different spectra. So can you say a little bit more about that?
Yeah, so you need to basically take the sources that are in the overlap between different surveys. So, for example, after you evaluate the model on one set of data, you take all of these same sources that have been observed by a different survey, and you can create a new model using these outputs as a training sample. Because you would know what the parameters for these sources should be, you can try to adjust the grid of the parameter space for the other survey in order to make it self-consistent.
And is there a way to combine, so for example, Apogee and Boss,
Uh-huh.
would you, can you imagine a combined model when the data exists for both stars? Is a unified
Yeah.
minimization there, or?
Yeah, it's non-trivial. It's really non-trivial because the data look very different. To some degree, it almost works. For example, there were a couple of times where we accidentally passed the wrong data through the model, and we were able to look at how the apogee network works on both data and vice versa. And obviously, because it's unfamiliar set of parameter space, machine learning is kind of like memorization of what type of features that you are dealing with. So it's not the resulting parameters were not ideal. It was still able to recognize some of the grander patterns. For example, it was able to see that if you have a lot of molecular lines, it's likely a cooler star. If you have primarily hydrogen lines, it was a hotter star. But the exact fine tuning really need to be able to train a separate model. We've tried trying making a more unified model, but it just really it's complicated. It's
Hmm. Hmm. All
maybe
right.
maybe someday.
Uh-huh. Uh-huh. Well, spectroscopic binaries then, and now I need to come back to the training set. So you're training on photometric data, as I understand. No, hang on. You
We're training on photometrically derived labels.
photometrically derived labels. So that's the first point. And then you have spectra on those, you train on those. But so, for example, spectroscopic binaries, do they, at the end of this, are you worried that they're present, or you know to exclude them, or you
I
can
mean,
find?
spectroscopic binaries are fairly rare, so they are about 1 to 2% of the total sample. So they're not going to skew the weights too much, even if they are present in the training set, because the bulk of the data are still going to be single stars. We've looked at the parameters that are produced for the sources that we do know that are spectroscopic binaries. There are not very strong biases in the parameters that we derive for SB2s versus regular single stars.
Why am I think? Well, perhaps I don't mean spectros, just binaries in general that
Mhm.
are photometrically present, but they're in this. I guess I mean a lot of traction systems are binaries, so it's just I guess secondary you're saying is often irrelevant.
Yeah, if the secondary is significantly fainter than the primary, I mean, you wouldn't necessarily have a significant concern, even if it was more traditional methods. It's primarily SB2s where you have strong signature from the other star in the spectra that you really need to worry about. But again, there might be some systematics that are produced by them, but it, these systematics tend to be fairly minor. We do hope to be able to expand this approach to SB2s in the future. Now that we do have all of these parameters that we have been able to derive, we would be able to create empirical templates for the entire parameter space, and we'd be able to basically reduce the cross-matching to search for SB2 specifically.
Hmm. Hmm. Well, again, people should raise their hands if they have more methods questions.
Yeah, Jonathan, we have a couple questions in
Oh
Virginia.
yeah, please go ahead.
So you'll just speak up because the microphone's over here.
Okay. Yeah. Marina, thank you for the great talk.
Mhm.
So I was wondering, while you are training your model for the Gaia data, have you ever cross-matched it with other catalogs? For example, the most or SDSS?
I mean, yeah, that's how we needed to, that's what we needed to do to be able to train this model. We took the parameters that we have gotten from LaMost and SDSS, and we have been able to apply these parameters as a training set for Gaia data.
Have you cross-matched with other catalogs as well?
Um, Less so with other surveys because generally they tend to avoid the galactic plane, so they don't really observe young stars. So potentially it would be possible to do it for other surveys, but because the here we can ensure that the parameters that we derive from all of these pipelines are self-consistent. We can't guarantee that the parameters from other pipelines would be quite as self-consistent, but um, generally, I mean, people have been able to identify, at least overall, here are red giant stars with these parameters. There have been efforts by the surveys as a whole to try to ensure some self-consistency.
Do you have diagrams that show? I like to see scatter plots where, well, I mean, there's a training step where you're predicting something that you know, and then you do it, of course, on seeing the data afterwards. But do you have any example plots like that, or even?
Give me a second. I can pull up some it in the papers. I don't have it in the presentation itself.
Just to get a sense of what you think the accuracy would be on. I'm trying, if we use this, what do we expect the accuracy to be on some of these parameters, like, I don't know, age of a pre-main sequence star, or I think you mentioned metallicity is another parameter you can derive.
Yeah, give me a second to pull it up. So here, let me share it again. Okay, now can you see it? So this is the paper that is overview of epigenetic Boston, and here you can see the scatter in the uncertainties for temperature, surface gravity, metallicity, and radial velocities. So for the most part, the overall distribution of uncertainties is what you'd expect. It's for temperature, it's lower for lower mass stars because you have more lines to be confident of your temperatures. It is a bit higher for the high mass stars because lines become sparser and more rarer and more broad. And again, these uncertainties, if you take a scatter across all of the different visits, it's just a perfect Gaussian. And the width of this Gaussian is 1 sigma.
Right. Okay. So log G, I mean, it sounds like log G could be better than for pre-main sequence stars. Then are we in a regime where you think log G is better than the photometric markers then, or?
I do think that it is much easier to work with surface gravities than it is with photometry because you don't need to worry about extinction. At least the actual scatter in log G, I mean, usually we can get it to around 0.1 dec, so it's not quite as precise as you can get photometry, but again, it's just easier to work with.
So let's see then. So how accurately can we measure ages and relative ages then? What's the summary? Would you say?
Going back to here, so probably something on the order of 0.1 dec.
All right. Any other questions on methods before we go on to some of the interesting things you were finding about the young stars?
We have a quick question from Ayush in here.
I think my question is.
So you have to speak up.
Yeah, I think my question is more about the results though. Regarding the disrupted population that you're showing on here, I have a basic question: why were they not showing up in photometry, but now they're showing up in spectroscopy?
Oh yeah. So the reason why it let me pull it up again. Come on, here we go. So the reason why it showed up here and not here, well, how young populations usually are identified is through clustering. So because you don't have kinematic coherence, we couldn't see it in cluster sample. And here you tend to have slightly higher extinction than in the rest of the galactic plane. So when you have higher extinction, it just becomes much more difficult to identify sources photometrically as well. So that's why we have been able to, we have missed it here, but it's out fairly clearly here. It would be good to confirm this population by other means. For example, if we have a whole lot of optical spectra toward these sources, if we see other signatures of use, for example, if we are able to confirm the presence of lithium, this would be a fairly unambiguous confirmation that these sources indeed forming the young population. I've racked my brain trying to figure out what systematics might be causing this population to just appear. Maybe we're just deleting ourselves, but I can't think of anything. So
Do you have lithium already from BOSS? Do you have BOSS spectra of these objects?
Unfortunately not. So this is fairly recent. We have only been able to find this population earlier this year, and the targeting for BOSS is, I mean, it's fairly late in the survey, so these sources haven't really been included.
But what does the Gaia kinematics say about this population?
I mean, proper motions are completely incoherent. Radial velocities, I wouldn't trust Gaia radial velocities at this point, at least not for pre-mean sequence stars.
But are they expanding? Is the population expanding?
Sure. I mean, it's the stars are moving in random directions. They don't seem to be related with one another at all.
Well, that is very strange. I mean, you'd think there'd be at least some coherence on some scale between some stars.
Absolutely nothing. Absolutely nothing. A hint of this has been identified in one of the catalog for clustering trying to study SCOSEN, but it just was the least significant group, and just a couple of dozen stars, maybe slightly, just barely co-moving, but definitely not this entire thing.
Because that's huge on the sky. I mean, that's tens of degrees. You said 200 parsecs away.
Yeah.
I mean, there must be very accurate proper motions.
Yeah.
Wow, we should well, have to read this is published, is it?
Yes. Yes.
So we have to follow this up here. Yeah. Any other questions on the YSO structure kinematics that's coming out here? Are you fitting? Are you deriving radial velocities from the spectra? You have to remind me.
Yeah, we did it for BOSS spectra and for Lemos spectrum. We didn't do it for apogee because traditional pipelines that are processing apogee data tend to be fairly reliable. I definitely would prefer using radial velocities from traditional approaches instead of this. The only reason why we have really done it is because when dealing with BOSS and Lemos data, they have shared roots that date back to the Segway survey. And there have been some issues with the pixel scale on the blue end. So the radial velocities ended up being systematically shifted because of the calibration in wavelength. And so I wanted to have a self-consistent radial velocities, even accounting for the systematic offset. But for apogee, you don't need to do that.
Well, I mean, so other questions on this identifying young stars. I know we've chatted in the past about how good are the photometric variability results from Gaia that is claimed to be useful for finding young stars. Did you have a comment on that?
Yeah, I think that approach, so you need to be really careful about the extinction. And I think that specific catalog did not take into extinction as carefully as one needs to do to have a clean selection. So certainly it's able to identify kind of the most obvious candidates, but you have to be careful with trusting it to its entirety. Any from contamination.
Are you talking about the variability?
Yeah.
Methods? Because extinction would.
There are other variable stars than young stars, so it's still contaminated.
Okay. But this large population you found, is that the main one, or are there other regions here that are popping out?
So most obviously it's the main one. We haven't looked at them in more detail beyond that because this is once again fairly new. It's only came out earlier this year.
And to what distance then are you probing here, do you think, in this YSO population?
Here, probably, I mean, it should be comprehensive within around 500 parsecs. It's definitely less complete once you go beyond that because we are selecting explicitly low mass stars, and you're starting to lose them once you go to larger distances.
Any other questions about the young star science and results coming out here? I recall, Marina, in the past you have worked on connecting YSO kinematics to was it turbulence models of gas in the clouds, and Do you have a
Yeah.
comment on?
Yeah, so I mean, for the most part, when you do see coherence in the kinematics, so not on here, generally the kinematics of stars match the kinematics of the gas. But I haven't really done that in much detail. The one place where we have worked with kinematics recently, let me pull up that paper. Do I have it saved? Mhm. So there are some of the other oddball populations that we have stumbled across recently. Okay. So for example, here we were looking at CAM OB1, which is this was one of our targeting commissioning fields for SDSS. And this region is quite interesting because we have these 3 different clusters, or however you want to call them, 3 kinematically independent groups of stars. They are slightly offsetting each other in the plane of the sky, but they are relatively nearby. And they are well separated out in proper motions and in radial velocities. But if you try to actually project all of these populations backwards, and so here is the current position of all of these populations, this has been their trajectory over the course of their lifetime. They are kind of found right now in the interarm region, but this population in red seems to be coming from the other spiral arms. We tend to think about these as associated with the local arm. So there are some interlopers that we have been able to find that are we don't really know what is happening with them, why they're moving in the way they do, and it's just odd to have the collision of 3 different clusters at the same time.
Great. Any other questions about the star formation results? Right then, and then let's see. So in terms of stellar evolution, there are grids of when you said you default using the MIST models. There are some, especially in the pre-main sequence, there are some differences in the models. So I guess the question is, that's one aspect. So are the pre-main sequence models able to be improved now, given what's being learned? But at the same time, you're training, assuming the MIST models are right. So maybe that's one aspect we can think about. But then, more generally, are people developing spectroscopic or basically stellar evolution models that predict the spectra? So I guess there's 2 parts to this here.
So I mean, yeah, definitely there are various models of stellar evolution. So there are spot tracks, which probably work a bit better for the pre-main sequence stars because they infer that there is a second temperature component from the spot. I don't know what are the current updates on how these models are currently being improved, or if there are efforts to improve them, or what is the status of the latest efforts to improve synthetic template. But one of the ways that we could potentially improve them is lately I have been trying to measure radii of all of the stars. So if we were to take all of these stellar parameters for temperature and surface gravity and metallicity, and we kind of ignore the spectroscopy part of it, but we go to the photometry. We have broadband photometry across most of the optical and ultraviolet and infrared spectrum, and so we can fit the underlying SED using the templates for the temperature and surface gravity, and we can infer if we have the parallax towards the stars, if you know the distance towards these stars. We can measure extinction and we can measure the radius of the individual stars. And here you can see that all of the sources are color-coded by the radius. And if we have radius and we have surface gravity, we can also infer the mass. So we could potentially determine more parameters about all of these stars using combination of these parameters. So this was kind of very promising, being able to see that the stars that you expect to be larger are indeed larger. And so as we continue to play around with these parameters, maybe we would be able to provide even more data to the people who would work on the theory of atomic to produce these synthetic templates.
Great, very exciting. Very good. Then we're close to the hour here, so we'll, unless there's a burning last question, we're going to close the main session. So, not seeing that, let's thank Marina again. Thank you very much. And